Hello all, and today we shall continue with our discussion on this bar element. Oh, sorry, not bad element. It should be bar element. Damn autocorrect. Okay, so before we start our discussion, we need to adopt one sign convention, and the sign convention that we would be adopting is that anything on the right hand side of the origin that would be considered positive, and anything on the left hand side of the origin that would be considered negative. This is our origin. So here we are considering a bar element of total length L. This is our node 2, this is our node 1, such that at node 2 the force that is acting T, it is on the right hand side, and at node 1 the force which is acting, that is acting on the left hand side. And because of this tensile force at the two ends, what would happen is that the bar element which was earlier of length L, now its length would increase, and let's say that the total length now is L dash, such that the node 2 has moved in this direction from its original position by u2 amount, and node 1 has moved in this direction from its original position by an amount u1, and see L dash is the total length. Okay, the total length is L dash, and the distance between these 2 points is still L. So we can say that L dash is equal to this length L plus C u2. This is on the right hand side of this original position, so it would be considered as positive, plus see this u1, it is on the left hand side, right? And according to the sign convention that we have adopted, anything on the left hand side is considered to be negative. So if we just add along with this sign convention, then the total length L dash would be equal to L plus u2 minus u1. Therefore the total strain for this bar element is the change in length divided by original length. Now substitute the values of L dash and L, and we would get epsilon to be u2 minus e1 divided by L. Next, remember, this would be our one very important expression that we shall be using in a few minutes time. Another one is that the relationship between stress along x direction, because we are considering a linear case here, is equal to Young's modulus multiplied by the strain in the x direction. Let's say that it is epsilon x, because we are considering only the cases that are happening in the x direction. So we can say that epsilon x is equal to E multiplied by u2 minus u1 divided by L, and this is our another expression that we shall be using. The third expression is that we would require that, say, if we consider that this particular bar, it is having a cross sectional area A. Then cross sectional area means the area which you would be seeing for this bar element when you would be looking from this this sidewise, from this side or from this side, whatever area that you would see, that would be the area of cross section. Okay, so see, here we are considering the area of cross section to be A, and the relationship between a force and area of cross section is that we need to multiply area of cross section by the stress in that particular direction to get the force in that direction. So we want to find out the force that is acting along the x direction, or we just want to relate the force in the that is acting the x direction with the area of cross section of the bar on which this force is acting. Then we need to multiply the area of cross section by the stress that is acting along this direction to get the force T which is acting along horizontal direction here. So now we can say that we can relate this T with these nodal displacements by substituting the value of sigma x from the earlier calculation. So we can write T equal to A into E multiplied by U2 minus U1 divided by L, or we can say that we have got one very important relationship, T equal to A let me write it in a different place. T equal to A into E divided by L multiplied by U2 minus U1. This is the relationship that we would actually use for our further calculations. And let me rub all these things because I need this space. Okay, now once we move to the nodal cases, then see the force which is acting at node 2, the force which is acting at node 2 along x direction, that is equal to T, and since it is acting on the right hand side, so as per our sign convention, that would be considered positive. Similarly, the nodal force which is acting at node 1 in the x direction, that would be considered minus T, as that is acting on the left hand direction, and as per our sign convention, that should be considered negative. Okay, so now we can say that when we consider nodal cases, then the relationship would be F1 x equal to minus T equal to if we just rid of the screen once, A E divided by L multiplied by U2 minus U1, or we can say T is equal to minus A divided by L multiplied by U2 minus U1 when we are considering node 1. Similarly, when we consider node 2, then it would be F2x equal to T equal to A divided by L multiplied by U2 minus U1. So now if we just write the entire thing in a matrix form, and remember, matrix form is the basic form of any finite element method. Of this entire finite element method or finite element analysis is based on this matrix calculations. So in the matrix form, it can be expressed as f1x f2x equal to AE by L into 1 minus 1 minus 1 1 into U1 U2, and this form, this entire form is very similar to the form that we have already studied in our spring element classes. And if we just draw an analogy between them, then it can be seen that this entire thing, A into L into multiplied by plus 1 minus 1 minus 1 plus 1, this entire thing is what is known as our stiffness K in this case, or this would represent the stiffness matrix. And these terms, when written in this column matrix form, they would represent the nodal displacements. And this would represent nodal forces. So this is all about our bar element when we are adopting a sign convention to find out the relationship between nodal forces and nodal displacements. See you in my next video.